we know how to deflect asteroids. Let me tell you the problem. How do you deflect something that you don't know exists? Or when I say don't know exists, meaning you don't know where it is, right? There's nothing you can do if you don't know where it is. So let me just show you a little bit about what we're doing. Well, first off, B612 Foundation. B612 comes from the home of the asteroid home of the Little Prince, which is a favorite book of mine. And so there's the Earth. This is what we are trying to protect. I tell people, I go, that's a nice planet you've got there. It'd be a shame if something happened to it. And the point I want to make is it's really in our hands. We're at the point where we can actually protect this thing. We have the technology to do this. So when I said, how do you give an asteroid a millimeter per second of delta V? You run into it with a small spacecraft. Calculate your delta V, which is just an MV, typical impact speed, 10 kilometers per second. There you go. So let's spread out from the Earth. There's the Earth. Is there a pointer up here? That's it. Ta-da. There's the Earth orbiting around the sun. Here's the big picture of where we are. So we go around the sun, and what we've done is we've shown here all the known asteroids. And these are anatomically accurate. We took them from the JPL database. This was a big compute project. Every one of these things is accurately depicted. Okay, that's the asteroid belt. Here are what are called the near-Earth asteroids because they come near Earth. It's like 2012 DA14, right? So one of these is 2012 DA14. I don't know which one. There are 10,000 near-Earth asteroids. Again, this is all anatomically accurate. There's the Earth whizzing around. I like to tell people it's like we're driving around in the solar system blind because we know what volume of the space that we've observed with telescopes. It's about 1%. So that means there are really 100 asteroids for every single one that's here. So what you can do is you can picture that. You can multiply this distribution by 100 and you see what the real solar system looks like. Looks like this. So we've just taken the known distribution, all the known asteroids, multiplied that distribution by 100. And there you go. That's what the solar system looks like. When I say we're flying around the solar system blind, that's what I mean. 99 out of 100 of these are unmapped, uncharted. Okay? And these are the ones larger than the one that struck in Tunguska. So I've taken, my arbitrary limit is 10 megatons, and I said anything below that I don't care about. I'm just going to cut it off there. I submit to you that a 10 megaton explosion randomly somewhere on the surface of the Earth is something that we ought to strive to protect. My feeling on it. So what are we going to do? We're going to launch a space telescope. It's called Sentinel. And we are going to fly it inwards in the solar system. We're going to go past the planet Venus. That was it. This is Sentinel right here. Its launch date is 2018. For scale, this is about 25 feet high, so it's about the size of a moving van. Person's about that big. It is a redesign of the Kepler Space Telescope and the Spitzer Space Telescope, which is an infrared space telescope, both built by a company called Ball Aerospace. That is its orbit. This is Venus. So its orbit is very close to Venus. So it's orbiting the sun. There's the Earth again. Remember, light green is the Earth. And it orbits the sun. Why do we want to be there? Well, because remember that any asteroid that hits the Earth has to cross Earth's orbit, and therefore it spends part of its time interior to the Earth's orbit. That means if you want to find it from Earth, you've got to look towards the sun. That's tough. So we're going to put our spacecraft, our space telescope, somewhere closer to the sun, looking outward.